So, in the previous video, we kind of just briefly glossed over the notion of divergence and convergence of limits at infinity. And so, what we're going to really do in today's video is we're going to sort of formalize this notion a little bit. And what I really want to kind of convey is the fact that even if a limit isn't at infinity, it can still diverge, which we've seen previously when we have limits at asymptotes. And also, certain limits at infinity can converge, which we also did see in the previous video. So over here, we have kind of a very basic definition of convergence. Again, these are all just solely calculus 1 based definitions of all of these notions. And so if we have the limit as x approaches a of some function f of x, and we define that to be equal to some real number L, and we kind of put this little constraint here where L has to be finite. It can't be equal to plus or minus infinity. And it has to be like some particular value. L can't this limit can't really oscillate between two values. It has to be one definite value. It has to be finite. Then we say that this limit over here converges to L. And so, we've been dealing with a lot of convergent limits. I mean, when you just input, by direct substitution and we would get some particular number out, then we've been kind of dealing with convergent limits without really realizing it. The notion of a divergent limit, though, that's one that's a little bit newer to us. But, I mean, we've even saw some concepts of a divergent limit. So when we take, the limit as x approaches 0 of 1 over x, and we say that this is going to be equal to plus or minus infinity, right? So this over here, we would say that this thing diverges because, it actually does not satisfy this first criterion over here. And so this limit diverges, and we saw graphically what that means is that this limit just asymptotes towards plus and minus infinity. However, one thing to note is that this condition over here that we discussed where it has to be one definite value can also cause certain limits to be considered divergent. So if we want to think about an example of that, one of my favorite examples actually is the limit as x approaches infinity. And we're going to use sine of x, but you could also think about maybe cosine of x as well. Now, we know sine of x is going to oscillate between 1 and 0, or sorry, negative 1 and 1. So it'll be between negative 1 and 1, right? And so we know that this limit as x approaches infinity is going to have to be between negative 1 and 1. But we don't necessarily know whether or not it's going to be equal to 1, or if it's going to be equal to negative 1, or if it's going to be one of the values in between. Maybe it could be 0. We don't necessarily know because this notion of infinity doesn't, it's a very abstract kind of concept. It's not like you can necessarily plug in sine of infinity. But, theoretically, if you could plug in sine of infinity, then you would get something within this range over here. However, we're kind of oscillating, right? Because it could be one of these values, it could be anything in between. So we know the bounds of this limit if you want, but we don't necessarily know what this number L is, at least in this particular scenario. So we can also say right over here that this limit diverges. It diverges even though it doesn't go off to infinity. I mean, it's bounded over here by negative 1 and 1. So we know that it won't just arbitrarily, asymptote towards infinity as we saw with 1 over x over here. But we also know that we aren't really going to approach one particular value. We're kind of just going to continuously oscillate, and we don't necessarily know whether we're going to converge to negative 1 to 1 or anything in between. And so another example that we can think of is something that actually, diverges even though, I don't know how to explain it, in the sense where we have a numerator and a denominator, a rational function where both the numerator and the denominator diverge. However, we have this notion of, I'm actually going to arbitrarily switch colors because why not? We have this notion of kind of how fast a function diverges, right? And so one very good example of this would be the limit as x approaches infinity of e to the x over x squared, right? I mean, we look at this, if we, supposedly input infinity into this function, we're going to get essentially infinity over infinity. We're going to get both of these things diverge, and they both do diverge quite quickly. However, the way that we would approach evaluating this limit, I mean, we can't necessarily input infinity into the function, but what we could do is we could think which one is going to diverge faster. And we know that e to the x right over here, as x approaches infinity, e to the x will we can say will grow faster than x squared. And I mean, we can just observe this because here we have an exponential, here we have kind of a quadratic term. And so because of that, we can say that this thing right over here is also going to be equal to infinity, and this is going to diverge. So this diverges over here. And the reason it diverges is because even though we have the numerator and the denominator, they both diverge, so maybe we could say like this is some sort of indeterminate form or something. One way to think about it is e to the x is going to diverge significantly quicker than x squared, And so this is one particular example of divergence. And if we were to take the limit as x approaches infinity of the reciprocal of this, let's say x squared over e to the x, then it turns out that this one will actually converge. And the way that we can think about its convergence is, again, we have x squared and e to the x. These are both going to diverge as x approaches infinity. However, x squared is going to diverge significantly slower, or is going to grow significantly slower than e to the x as x approaches infinity. I mean, if you want to think about it, 100,000 squared is going to be less than e to the 100,000th power, right? So essentially over here, we could say that this thing, e to the x is going to grow significantly larger, so as x approaches infinity, this thing is going to converge to 0. So this thing right over here converges. And so essentially, we've kind of noticed a little sort of pattern over here. Is we have to kind of just think about how fast certain functions can diverge when we're thinking about rational functions, and that can help us determine whether or not we're going to have a convergent or a divergent limit. It's just thinking about whether the numerator is going to grow faster than the denominator. And, of course, sometimes it can be very difficult to tell. Like if we have the limit as x approaches infinity of like e to the x over x factorial, these are both going to grow extremely quickly. And so it's very difficult to determine these types of limits over here, these kinds of, circumstances. However, when you have something like this, we can immediately tell that the exponential is going to grow significantly larger than the quadratic term, and that can kind of help us determine whether or not our limit is going to diverge or converge. So this is just a very kind of basic introduction and kind of overview of the notion of convergence and divergence of limits. And we saw over here that we don't necessarily have to have a limit at infinity in order to diverge, right? Not only that, but we also don't necessarily have to have the limit being equal to infinity to be considered divergent, like we saw over here in the sine of x example, where we still managed to diverge as x approaches infinity because we didn't approach one value, even though we were bounded by two finite values. So whatever value we do approach would have to be finite. We don't exactly know which one we're going to approach. We don't know where we're going to end up converging to. So we say that it diverges, even though it is, it would be finite, theoretically. Meanwhile, over here with 1 over x, we said that this thing diverges over here because we approach an infinite value. It's not a finite number. And we also noticed that it was as x approaches 0, so we don't necessarily have to say as x approaches infinity. And you know what, as a little kind of just thing to conclude this, why don't we go ahead and take a look at the limit as x approaches infinity of 1 over x. And so this thing right over here, again, you can think about this, and you can try kind of direct substitution. You can take like 1 over 100 trillion, let's say, and that's going to get very, very close to 0. And so this thing right over here would be equal to 0, and so this would actually converge. And again, you can look at this graphically, you can see that we asymptote towards 0 as x approaches infinity. And so we have a very interesting kind of behavior with 1 over x, is that as x approaches infinity, it actually converges to 0, but then as x approaches 0, it actually diverges to infinity. So we have some very interesting kind of ways of determining function behavior by looking at, we can kind of say like the end behavior of different functions, and that's kind of through taking limits at infinity.